In this video, we are going to take a look at the ideal gas law and its application. Please read the OER textbook chapter section 9.4 for more detail and start working on your homework as soon as you finish the video. In the previous video, you learned about the relationship between pressure, volume, mole of gas, and temperature, and also you're looking at the kinetics molecular theory that is used to explain those behavior as well. Okay. In this video, we are going to combine all these simple gas law together of this relationship that we learn, right? Which is going to be related to all of these equations that we see from lecture 9.2. Okay, we're gonna combine all of these together. Okay, so we're gonna combine them. As we combine them, we are going to get the PV equal nRT as the ideal gas law equation. Okay, so this is going to be used only for gas. Okay, so and also with the ideal gas as well. I'm gonna state what is the ideal gas. Okay, so pretty much this PV equal nRT, some people call it PIV nerd, is going to be used when you are having the gas that you need to deal with. The R is going to be the constant with this unit. Okay, so later on, you're gonna learn the different number and also different units for R. R is what we call the ideal gas law constant. Okay, so it's 0.0821 liter times ATM times mole and times Kelvin. All these units that you are going to input into this equation have to be based off the R unit. Okay, so that means in this case, pressure have to be in ATM, right? Volume have to be in liter, and N have to be in mole, and temperature have to be in Kelvin. Okay, so because everything have to base on the constant unit. Okay, so just note that. So you don't need to memorize this R constant on the exam. It will be given to you. Okay, you just need to know how to use it. Okay, so now to talk about the ideal gas real quick. So what is the ideal gas? Okay, so the ideal gas is based on the assumption that come from the kinetics molecular theory that we learn from from the previous chapter video 9.3. Okay, so what are the assumptions? Then one is the gas molecule do not interact with each other, right? So therefore they would not, if they collide, they would not lose kinetics energy, right? So that means the energy would remain through like the same energy throughout the whole container, right? So they do not interact. They would not lose any energy, and also the size of the gas particle is very, very, very small compared to the volume of the container. So therefore, in this case, we can imply that the volume of the gas would be the same as the volume of the container that that gas is inside. Okay, so that means in this case we can use this to use the fact that the volume of the container would be the same as the volume of gas in this case. Okay. All right, so when to use all of this equation then? So to answer this, I want you to jot this down, okay, because when you are going to see problem on the exam, you need to know exactly what type of equation you need to use. Okay, so whenever that you are given gas problem, okay, so anytime you see gas, right, pressure, volume, or whatever temperature, this is going to be one of these equations that you need to use. Okay, so when there are two conditions given, then you are going to use this simple gas law that you learned in chapter 9.2. Okay, so but when there are only one condition given, like only one value of the pressure, one value of volume, one value of temperature, or one value of mole, this is going to be the one that you are going to use, which is the ideal gas law, which is in this chapter 9.4 that we are learning right now. Okay, so I want you to differentiate that first. Okay, so let's take a look at example here. So an example is, for example, one, right? So it's giving you volume in this case, it's giving you mole, it's giving you temperature, asking you pressure. So in this case, there is no two value of anything, right? So everything are given in just one value of volume, one value of mole, one value of temperature, and also asking for one value of pressure as well. So that way, so in this case, what we are going to use is going to be this one condition given, which is PIV nerd, that we are going to use PV equal nRT. Okay, so in this case, we're gonna use PV equal nRT to help us. Okay, so we're gonna, what am I doing first is I'm going to move volume to the other side of equation because I want just the pressure at the end. So if I do that, I'm going to get pressure equal to nRT over V. Okay, so then I'm gonna plug all those value in, right? So remember mole, right? So if the problem giving you not in mole, if it's give you in grams instead, you will need to actually convert that to mole first, okay, by using molar mass that we learned in Chem 121. Okay, so this is Chem from Chem 121. Okay, so you need to recall that. Okay, so it's changing from grams to mole using molar mass. Okay, so that's from 121. In this case, you don't need to do anything because it's already given you in mole. So perfect, we're just gonna use that. Okay, so it's already give you in mole. The next one is the R value. So R, I want to recall the math, a little bit of math here. So just for you to not be confused, the unit of the R as you see in the previous. Okay, so these two values are both acceptable. Okay, just one are more precise than the other, right? This is more precise because it's more significant. Okay, the unit, okay, so the unit can be written as, you can see ATM times liter over mole per Kelvin. You can write this way, or you can write as, because when anything is per, is under division, the exponent of that would be a negative, right? So that means in this case, you can also rewrite as ATM times liter times mole to -1 and times Kelvin to -1. These two, okay, also identical as well. Okay, so either way, you can use either way to set up your calculation here. Either way should be correct. Okay, so in this case, if you looking at this, you can cancel mole, right? Because mole, this is per mole, you can cancel it. Okay, same thing for temperature as well. You have Kelvin and per Kelvin, you can cancel that as well. Look at this way, right? So if you are confused, okay, so it's the same as this, right? So pretty much you are canceling this mole and this mole, right? This Kelvin with this per Kelvin. Okay, so that's what we are doing so far. Okay, so and then you are going to divide that by liter, and you will see that the liter will cancel each other out. So at the end, you are going to end up with the pressure in the unit of ATM. Okay, so is this our final answer? The answer is no, right? Because 1 in torr. So therefore, in this case, you will need to convert from ATM to torr. And according to our first lecture 9.1, we know that there are 760 torr in 1 ATM. So therefore, in this case, you are going to get 1.24 times 10 to the 3rd torr for the pressure. And all of these are 3 sig fig. Okay, so that means 3 sig fig would be the one that is going to limit the number of sig fig at the final answer. So we have only 3 sig fig here. Okay, right. So let's take a look at next one. Okay, so the next one, what about if you are given 2 conditions, but we have to deal with more than 2 variables? So before, if you're looking at the simple gas law, right, you can see that it's P1 V1 equal to P2 V2, and then we also see as well that V1 over N1 equal to V2 equal over N2, and so on, right? So we see that. What about if we have the 3rd one introduced into it? Like, what should we do? Okay, so in this case, what you are going to do is that you are going to pretty much rearrange this in order to get the 2 conditions. For example, if the equation giving you the fact that, let's say like the temperature is constant, everything else is not going to be constant, it's going to change, right? So let's say like if the problem that is given, the only thing that is constant is temperature, what you are going to do is you are going to move everything that are not constant to the same side and leave the thing that are constant with the same side. Okay, so in this case, if we have temperature constant, what you can do is that I'm going to move P, V, and N to the same side, right? Because all I need to do is just divide both sides by N. So if I do this, the other side that I'm going to have is going to be R and T, okay? As we know, R and T is the constant, so it's never changed. So that means if you have condition 1, okay, so let's say P1, V1, and and N1. Okay, so this going to imply the first condition. If you change all of these, then the new condition is going to equal to this constant. Also, remember the constant would never change. So that means in this case, the second condition P2 V2 over N2 would equal to this constant. Therefore, in this case, what you can say is that you can also use P1 over, V1 over N1 equal to P2 over, times V2 over N2. You can do that as well. Okay, so this is a scenario where you have the temperature being kept constant. Now, what about if I have pressure constant, for example, what should I do? Okay, so I'm just gonna give you a second scenario. You can do with any of this, okay? You can do with any of this being constant. I'm just gonna give you two so that way you get an idea, okay? So what if pressure constant? Well, if the pressure constant, then all you need to do is you are going to move the pressure to be the same, what do you call it, to be the same with the constant, right? So in this case, the R is a constant. So what I'm going to do is I'm going to rearrange that. So what I'm going to get is I'm going to get V over NT, right, equal to R over P, right, as the constant. So again, this is the constant. Again, all I did is I divide both sides by pressure and I divide both sides by NT, right? So that's why you are end up with V over NT, and then you end up with R over pressure. Okay, so again, because this R over pressure is the constant, therefore in this case, we can say that if you give this as the first condition, the second condition would equal to the same constant. Therefore, in this case, we can say that the V2 over N2 and T2 would equal to this same constant. Therefore, what we can say that we are going to be able to derive that in V1 over N1 T1 equal to V2 over N2 T2. Okay, so why is this important? Well, let's take a look at an example. Okay, so let's take a look at example here. So this example is given the fact that scuba tank is giving you the volume of 13.2 liter. Okay, so this is the volume. Okay, and it's giving you the pressure as well. So this is the pressure, and it tell you that if the water temperature is at 27 degrees Celsius. Okay, so this is temperature, and asking you how many liter. Okay, so this is asking you how many liter, which is volume, right? So this is volume. Hey, wait a second, there are two volume here, right? This is volume, this is volume. So this is this problem involved with two condition in this case because there are two volume. So I'm going to give this as V1. This is going to be V2 that we are going to look at, right? And it's asking you how many volume of air which you know, like the tank will provide to a diver's lung at a depth of 70 feet, okay, in the ocean where the pressure is blah, blah. Okay, so that means this is the pressure. Well, we also have two pressure as well, right? This, I'm just going to give this one, this is going to be two. So therefore, in this case, we have two conditions. So we are going to need to use the simple gas law, but it's not only that, the temperature also change as well, right? So the temperature is not constant in this case, temperature also change. So therefore, in this case, what we are going to do is we're not going to be able to just use the simple gas law anymore because there are three variables that is changing. So in this case, what you need to do is you will need to, right? So let me actually list out all of this real quick. Okay, so pretty much this is what we want, right? So we have to set up, this is what we have to set up, right? So to set up those. What we are going to do is I'm going to rearrange this ideal gas law in order to match with all of those that are changing. Okay, so what I'm going to do is I'm going to start with, remember, because the only thing that is stay the same is the number of mole of gas, right? Because PV and T, those are going to be changed. So therefore, I'm going to move them to be on the same side. Okay, so in this case, I'm going to get that PV over T is equal to this constant right here. Okay, so similar to what I explained earlier. Therefore, in this case, I'm going to just give that PVT to be this one set of condition, which is going to be the first condition, and it's going to equal to the second set of condition. The reason why they are equal to each other because they are equal through this constant. Okay. So now what you are going to do is just plug in the value, right? So I'm going to actually get rid of these P2 and T2 first. because what I want is I want the V2, right? I want the volume, the second volume at the end. So I'm just gonna move everything else that I know to be the same size. So in this case, you're gonna cancel those two. And what you are going to do is you are going to get V2 equal to P1 V1 over T1 times T2 over P2. Okay, so this is, I'm just rearranging this. If you don't want to rearrange this, you are welcome to just plug in all the number right away and then solve for it. You are welcome to do that as well, right? So for me, I just want to plug all number all at once. So either way, which one ever that you are most comfortable with, just stick with that one. Okay, so if you want to plug all the value in first before you solve, that's fine too. Okay, so in this case, I just don't have enough space, so I'm just gonna rearrange everything so that way I can just have more space to write all this out. Okay, so I'm just gonna plug in the first pressure that's given with the first volume, divide by, remember the temperature have to be in Kelvin, right? So in this case, you need to change all of those temperature in Kelvin by added to 273, right? So, and then just make sure that you do with all temperature as well. Okay, so if you do that, you are going to end up having the volume to come out equal to 668 liter. Okay, so so that would be the final answer with the 3 sig fig. Okay. All right, so in this case, the next what we are going to take a look at is we are going to see more DIY problem here. So I would like you to actually make sure that you complete this on your own, and you can start working on your homework, chapter 9.4 as well. And you will see that the Moodle homework, some of them might give you the condition that where you will need to do some rearrangement of the ideal gas law to get this type of equation as well. Okay, so you get to practice more from the Newton homework as well. Okay, so after you finish a DIY problem, please check your answer against the key. Okay, so I'm going to post the key for this as well. All right, so the summary of this, what we see so far is that the Pfiffner on the ideal gas equation, this one here is derived from those simple gas law that we learned from chapter 9.2. Okay, so it's come from that. All right, next, if you would like to pause the video to actually complete the DIY problem first, you are welcome to do that. Okay, so and then resume anytime you want to, or if you want to take a break, you are welcome to do that as well. Okay, so just a reminder for that. So the next thing we are going to take a look at is the standard temperature and pressure condition. Okay, so this is what we call STP. Okay, so whenever that I say STP is referred to the standard temperature and pressure. Okay, so we're gonna look at the volume of this standard temperature and pressure of 1 mole. Okay, so molar volume is referred to molar, right? So molar is mole. So similar to molar mass, right? When I talk about molar mass, it's going to equal to the mass of 1 mole, right? So it's the mass of mole. So that's why in this case, you are going to see like grams over mole, right? Because it's the mass over mole. So same thing, molar mass is mass of 1 mole. Molar volume is going to be the volume of 1 mole. Okay, so whenever that you see the word molar, it's going to be per 1 mole. Okay, so in this case, we're going to look at if you have 1 mole of gas, which is equal to 6.022 times 10^23 molecule of gas, right? How much volume is going to occupy at this standard temperature and pressure. That's what we're going to take a look at. Okay, so the standard temperature and pressure is going to be set at 0 degrees Celsius, right, or 273 Kelvin. Okay, so for the temperature, and the pressure would be at the atmospheric pressure of 1 atm. Okay, so these two are crucial because it's gonna help you to know as well, like when you are doing calculation, and I said that it's happened at STP, right? So you need to be able to refer to this condition. Okay, so you need to know and memorize this. Okay, so temperature, standard temperature would refer to 0 degrees Celsius, and standard pressure would be 1 atm. Okay, so if we want to calculate for molar volume at standard pressure and temperature, what I would like you to do is I want you to use PV equal nRT to calculate for this. Can you just go ahead, use this to calculate for the volume of 1 mole at this condition, please? I'm gonna give you a few minutes here. Once you finish, can you resume the video again? All right, let's take a look at your answer. Okay, so you might ask, okay, what should be P then? Well, because it states that it's at standard temperature and pressure, so therefore in this case, the pressure would be 1, right? So, and then because it's molar volume, it's the volume of 1 mole, therefore I'm just gonna add 1 mole right here, right? We already know R, and then temperature would be at 0 degrees Celsius, or you need to enter 273 Kelvin for the calculation. So if you calculate for this, you are going to get the volume out to equal to 22.4 liter. What does it mean? Well, it means that at this temperature, at this pressure, 1 mole of gas occupy 22.4 liter. That's what it tells you. Okay, so if you have this temperature and pressure, if you have 1 mole of gas, it's gonna occupy this much space. Okay, 22.4 liter. Okay, so again, this 22.4 liter can be used only at standard temperature and pressure. Okay, so that's I'm just gonna highlight that. Okay, because if you change temperature and change pressure, we already know, right? It's going to change volume as well. So therefore, in this case, you can use only this number with only this condition. Okay. All right. So the next thing we're going to take a look at is we are going to use that information that we just learned to understand better with different type of gas. Okay. So when you have the same amount of mole of gas, regardless the type of gas, you are going to see that they are going to have the same number of molecules, right? So we already know this from Chem 121. Okay, so the same different type of gas with the same number of mole would be the same number of molecule, because 1 mole is defined as 6.022 times 23 molecules. Okay, so in this case, if you're looking at this, right, the mass of all of this gas would not be the same, because different gas would have different mass, right? So for example, in this case, helium would be lightest, right? Oxygen would be heaviest. Okay, so it just comes from the molar mass that listed on the periodic table. Okay, so that means in this case, again, the mass of different type of gas would weigh differently, but the number of mole, if you are fixed just 1 mole, they are going to have, if you have the same number of mole, they are going to have the same number of molecules. Okay. If this gas right here are at the same temperature and same pressure, right, are in this case is at standard pressure and temperature, okay, you are going to be able to say that they all are going to occupy the same volume, because this volume right here is going to be per 1 mole of gas. So if you have 1 mole of gas at this standard temperature and pressure, you are going to end up having the same volume for each of those gas. So that means the size of the balloon of 1 mole of gas would equal for all of them, okay, regardless of the type. Okay, so that means we can use this idea right here to state that regardless of type of gas, right, same number of mole, same temperature, same volume, they are going to have the same, if it's same pressure, they are going to have the same volume. So let's take a look at the volume of gas 1 mole at non-standard temperature and pressure. Then, well, all you have to do is the same thing, right? So in this case, you are looking for molar volume. Again, molar mean 1 mole, right? The volume of 1 mole in this case. So all you need to do is you do the same thing. You're gonna use Prifnert again, right, to find out what is the volume of 1 mole of gas. Right, so pretty much you are going to plug everything in and solve for V, right? So in this case, because pressure that is given is in millimeter mercury and temperature given is in degrees Celsius, so you need to convert those units first. Remember, the unit have to be matched with the unit of the R constant. So in this case, you are going to make sure that the pressure is in atm and the temperature is in Kelvin. Okay, so if you do that, you are going to pretty much get 310 Kelvin as the temperature and 0.8447 as the ATM. How did I get this at 0.447? Well, this is coming from the fact that you set up for 642 millimeter mercury, right? And then we know that every 760 millimeter mercury is equal to 1 ATM. Okay, so if you do that, you are going to get 0.8447 ATM. Okay, if you plug all of this in, you are going to get the volume come out to be 30.1 liter. Again, the reason why it's not equal to 22.4 is because the 22.4 liter, this is only applied at standard temperature and pressure for 1 mole of gas. Okay, so if you change temperature and pressure, the volume will also be changed as well. Okay, so that's why you see the volume are not equal to 22.4. All right, so this, what does it mean then? Well, it means that 1 mole of gas at this condition right here is occupied 30.1 liter. Okay, so that's what it tells you. Okay. All right, so if you want to pause video and then try to complete your homework for that section, you are welcome to before you start the next. But the next thing I'm going to look at is I'm going to look at the application of the ideal gas law. Okay, so we are going to look at the gas density and also molar mass as well in this case. What I'm going to do is I'm going to combine 3 equations that we see here. Okay, one is the density. We know the density equal to mass over volume, right? And we also know the ideal gas law as well, which is the Pfeffner, right? And then we know that the molar mass, which is this italicized capital M right here, is equal to mass over mole, right? Which is, in this case would be grams per mole, right? So mass over mole. So what I'm going to do is I'm going to combine these and rearrange them. Okay, so if I combine these and rearrange them, I'm not going to go over the detail, but pretty much what you are doing here is that you are starting with the ideal gas law, right? So you move everything so that the number of mole is only by itself. Okay, so then you are going to replace the number of mole, right? If you're looking at this, right? So this is number of mole here. If you rearrange this, number of mole that come from molar mass is equal to mole over molar mass. Okay, so if you do all this rearrangement, what you are going to get and what I want you to take it away from this is going to be this equation right here. So this one is going to be given on the exam, but you will need to know which each of those term are. Okay, so this part right here would not be given. So it's going to be given only the equation. So in this case, you just need to know what each of those term mean. Again, you do not need to know how to derive it, but you just need to know how to use it. Okay, so pretty much if you combine all of those 3 equations that I mentioned, you are going to get that the density of the gas would equal to pressure times its molar mass divided by the R constant and the temperature. Okay, so in this case, this equation right here is going to work only with gases. Okay, so you cannot use this with liquid or anything else. It's only applied for gases. Okay, because it's derived from the ideal gas law, right? The name implies the ideal gas law is used for gas. Okay. All right, so let's take a look at how to use this equation. Okay, so for example, the problem might ask you to determine density of xenon gas at a pressure of 742 millimeter mercury and temperature of 45 degrees Celsius. So again, if you're looking at this, it's always involved with the R constant, right? The R constant is in the unit of ATM time liter per mole per Kelvin. So therefore, this unit right here need to be converted so that it's matching with the unit of the R. So don't forget that. Okay, so that means in this case, if you do that correctly, you're gonna get pressure into ATM and then times the molar mass of xenon. Okay, so if you look at the molar mass from the periodic table, this is the molar mass of the xenon. Okay, so and then divide that by R constant times temperature. Again, let me remind you again. So the R constant on the exam, it would provide you with less precision. So you also can see it as 8.2, 0.821 as well. So those two is equal to me. One is more precise, one is less precise. Okay, so you can use either one of those. If you plug off this in, cancel all the units, your unit is going to come out to be in grams per liter. Okay, and because this problem doesn't specify the unit of density, you can leave this as it is. You can leave it as just grams per liter. But if the problem asking you to specify the unit as grams per milliliter, then you just have to convert this liter to milliliter later. But in this case, it doesn't specify the unit, so I'm just going to leave it as gram per liter. Okay. All right. I would like you to do example to yourself. Okay, so I would like you to think about diatomic gas that are in this group. right? And then I would like you to think about is given density and this condition right here. I want to know what is this unknown gas is. So what I would like you to pause the video now and then start this problem and then resume the video again when you finish. All right, let's take a look at your work together. So in this case, again, because it's giving me density, okay, it's giving me density, it's giving me those pressure and temperature. So that means in this case, I can definitely use this for sure because it contains density, and we are talking about gas as well, right? And it's also, we would know temperature and pressure as well. So in this case, all I have to do is just plug those in. Okay, so I'm going to rearrange the equation real quick because what I don't know is the molar mass, because it's given density. We know what is STP is, right? So we know those. So that means the only thing we don't know is the molar mass. Okay, so the molar mass should tell us the identity of the unknown gas. So therefore, in this case, if you rearrange the equation, you are going to get molar mass equal to density times the gas constant or times temperature divided by pressure. All I have to do is just plug in, right? So plug in density, plug in R value, plug in temperature, which is at 273 Kelvin for standard temperature, and pressure would be 1 atm. Okay, so even if pressure is 1, you still need to add that in your calculation, because if you don't show me that, you're gonna get point deduct from your exam. Okay, so if you're looking at all these units, you will see that the unit cancel out, right? So liter cancel out, okay, atm cancel out, Kelvin per Kelvin cancel out. So you're gonna get grams per mole left. So that means in this case, molar mass would come out to be grams per mole. And it's come out to be 70.6 grams per mole. Okay, how do I know then which one it is? Well, remember it said that it's in group 7A and it's diatomic as well. What does it mean when it said diatomic? Diatomic means 2, right? So that means if you're looking at diatomic gas in group 7A, you will see that chlorine, if you add 2 chlorine together, right, because it's specified that this is diatomic, is the two atom of that molecule, right? So that means in this case, this molar mass right here composed of 2 atoms of that particular element. So in this case, if you add the chlorine together 2 times, right, you are going to get 70.9. So therefore, in this case, we can say that chlorine is the identity of this unknown gas. Okay, so that's the answer for that. So the summary of this lecture section is that you learn the ideal gas equation, PV equal nRT, right? You learn how to do calculation for that. And then you're looking at the standard temperature and pressure. You're looking at the molar volume, right? Volume of 1 mole. And you also look at the application of the ideal gas as well, right? So that's the summary of it, right? So pretty much you're looking at all of these. Okay, so the homework that associated with this would be part of the homework 9.4. Okay, so start working on your homework as soon as possible. And if you have any questions, please do not hesitate to visit me during office hour.